Oops, yeah. So let's remember the definition of the polar variety of a set is introduced by Bernard Tessier. So we want to look at this slide here. Yeah. And so what Tessier suggests doing is taking the appropriate projection and then looking at the critical set of that projection at the regular points and then closing it up. So we're going to do that with the example of x defined by f of x, y, z is equal to z squared minus y squared minus x squared. As I said yesterday, in these simple examples, simply by looking at the two-dimensional rendering of the three-dimensional figure, you can see the polar curve. It's just the apparent contour, or at least the apparent contour is part of the polar curve. Maybe there's more hidden. But anyway, if it's a nice picture, you see the whole thing. Now let's see how we actually verify that. So we take a nice projection. We form a new map. And we look at the Jacobian matrix of this. And then we have the partials of f, 2z minus 2y and minus 2x. Well, the points where this has rank 2 it's 2, well, it's always 2, but it means that the kernel, I mean, it's always at least 2, but it means that the kernel of this projection has to kill the differential, so it has to be tangent. In other words, this is tangent. So it's picking out the points of tangency for us. We don't have to worry about taking closures here because the singular set is just an isolated point. So it's no problem. So we take the determinant of dg, and that's just 2z, plus or minus. That's the determinant of 2g, and then we have the equations. The codimension one polar curve of x defined by, first it has to be on x, so f equals 0, and the other condition is that 2z equals 0. And if we set z equal to 0 in this definition, we, oh, I think I messed this up. Sorry, this was x. I got them reversed. So the equation is 2x, and we see if x is equal to 0, then we just get a pair of lines. Okay. All right, so that's how you go about calculating polar curves. Now, and here I just described that a little bit. Varying the projection a little bit does not change the multiplicity of the polar curve, and Tessier showed that that multiplicity is independent of projection as long as you use a generic projection. Again, as I said yesterday, the codimension 0 polar curve is all of x. Now I want to talk about another way of constructing these polars, which will show us how to do it for modules. So the idea is that when we choose a projection, we're choosing a kernel. If we apply df to the basis of the kernel, then that's going to give us this many generic linear combinations of the generators of Jm of x. Then it's the size of the kernel. Put them into a matrix A. Take the points on the regular part where the rank of A is less than you would expect, G, and then take the closure. If we do the calculation, the point is that you're going to be looking at a matrix, and so the locus of zeros will be the expected dimension. So the expected dimension for matrices of this size, whoops, there. So the expected dimension of these guys is turns out to be L. That's the codimension, just as we hoped for. Okay, so now we can use a similar construction for the polar curve of a module. M is a module with generic rank G. Again, we take G plus L minus 1 generic generators of M, put them into a matrix A, take the points now where the rank of M is G, and the rank of A is less than G, and then we take the closure. Same construction basically as it works for sets. So here's an example here. This is one of my favorite examples. We want to calculate the polar curve of codimension 1. So we have to do the math here. No. This is, oh, I was there actually. Okay, so we have to do the math, and we have that, let's see, G, the generic rank is 2, and we need, our codimension is 1, and then we have to subtract 1, so we need 2 generic generators. The way to produce generic generators is you add in new constants, and then you take multiples of our columns. Now, M is going to have rank 2 except at 0, 0 for generic AB, so that gamma 1 is defined by the determinant. And again, if you just check this out, you just get a quadratic form, which if it's non-degenerate has two lines intersecting transversely. Here's another construction of the polar of codimension L. What we do is we claim that what you can do, you can intersect the progean of the Riesz algebra with X cross a suitable codimension plane and then projecting to X. And now you don't have to worry about taking closures. That's an advantage. Well, picking equations of H is the same as picking linear combinations of the generators of M. So here's an example. Supposing my plane H is given by setting these many coordinates on the projective space equal to 0. Then X cross H intersect the progean of Rn. Well, that's going to be points where some linear combination of the rows of M is 0 in the first G plus L minus 1 places. That's because these are 0. If I have a point of this intersection, these have to be 0. So those linear combinations have to be 0 in those places. Well, that's exactly a point where I'm in, that projects to a point in the polar curve. And then we have this nice feature that this shows clearly that if this is empty, then the fiber of the Riesz algebra over 0 has dimension less than G plus L minus 1. And that turns out to be very handy later on. So polar varieties of M control the size of the fibers of progean of Rm. And then there's one really important example, which I want to talk about a little bit. So here we go. Let's look at gamma d of the part of the Jacobian module generated by the partials with respect to z applied to xd plus 1. This is going to be a stabilization family. Okay. Now, we want to calculate this guy here. So we take G plus D minus 1 generators of the Jacobian module with respect to Z of curly X. Well, what is G? Well, the rank of JMZ of X is just the codimension of XD, right? Because I've increased the dimension of the domain by 1, and I have the dimension is increased by 1, so the codimension is the same. Okay, now this is equal to n minus d. So we need n minus d, that's the G, plus d plus 1, because the dimension's increased by 1, minus 1 generators. Oops, something went wrong. Oh, I see. Yeah, n increased by, no, this is G. Well, anyway, I might have done something wrong, but maybe I should have wound up with something like this, so I wound up with n minus 1. So it's n minus 1 generators is what we want. Now, let's think about what happens here. Okay. Suppose L maps Cn to C is a generic linear form. Then, if I look at the map, well, let's see here. So supposing X is defined by G. Then I look at the matrix of the map LG, I'm going to get something like, now let's assume that L for simplicity is just Z1. That's just to make things clearer. And here we have D of G. Across the top we have n variables. If I look and see where the rank of this is less than maximum, it's the same as looking at where the rank of this is less than maximum. If this is less than maximum. So this, of course, is going to be if I take the multiplicity of this set, well, this is going to be the polar of JMZ of curly X. On the other hand, this is looking for the points, this is looking for critical points of L restricted to the fibers. And so the upshot is that if I take the multiplicity of this over C, I get M. In this case, it's MD of X. It's the number of critical points. And Dirk raised the point that that we were originally working with what he called internal polar varieties. This is the closest example we have of a relative polar variety in this setup. Okay, so I think we're back to the slides now. Okay, so what we need to do is a way of relating the change in the multiplicity of the pair with our polar varieties. We're going to do that using the multiplicity polar theorem. And this is what it says. We start with a pair of modules where they're both sitting inside a free module. X is equidimensional fibers, Y is smooth. And M bar equals N bar of a set of codimension of set C of dimension K, which is finite over Y. All right, now we have the change in the multiplicity. So I want to look at the multiplicity in the fiber over 0 first. And then I want to subtract off what looks like an infinite sum, but it really isn't. The reason this is a finite sum is because this guy and this guy have the same integral closure, except at a finite number of points at most. So this infinite sum boils down to just the sum over the finite number of points where it's non-zero. And we have to take neighborhoods small enough so that we aren't getting extraneous data floating through. Okay. Then the theorem is that you can take the change in the multiplicity and you can write it as a change in the multiplicities over Y of these two polar curves. So let me try to do an example here. We'll see what comes out. As a way of understanding what we're doing here. Okay, so here the example is I is going to be the ideal generated by x squared, y squared. J is the ideal generated by x squared, xy, y squared. I'm going to get a family of ideals by just changing things a little bit. Let's call this y. This is going to be x squared minus y squared, oh, I better use t, after all. There we go. And j is going to be similar, x squared minus t. xy, y squared minus t. This is jt. Okay, good. I want to apply the multiplicity polar theorem to this family of ideals. So we have to do some more calculations. How about the multiplicity of ij? Does anybody see what that is? Once you have a little bit of experience, the answer is obvious. What do you think?
I would expect it's a difference in the length.
But the multiplicity is not the length. What we know is the lengths are different. The length of the co-length of this is the multiplicity, but the co-length of this is not. So what we want to do is we want to say that x squared y squared is a reduction of that, and therefore they must have the same multiplicities. And so E of ij is 0. So thank you for your answer, Matthias. That was useful. Okay, so this is 0. Well, how about what happens with jt when t is not equal to 0? What does this equal? Well, we see that if t is not 0, then v of jt is empty. There are no points. So in fact, if t is not equal to 0, jt is just equal to O2. Okay, that's good. And so that means the change, as I go from, what's my notation? Yeah, the change of jt is going to be 0 minus the multiplicity of O2. Well, that's just the multiplicity of the ideal IT. And that, if you count, you see you get 4 points, right? T is 1, you get 4 points. So this is 4. So this is an example where the change is negative. It shows the multiplicity of the pair is not necessarily upper semi-continuous. That makes life hard. Most of the proofs we use in the ISIS case fall apart now. Okay, how about the polar curves? All right, now you have to actually do the calculation out, I'm afraid. But if you look at gamma 1 of IT, I'm supposed to take 2 generic generators. Well, that's all my generators. Take 2 generators, see where they're 0, and I is not 0. The only place where my 2 generic generators are 0 is where I is 0. So the polar curve is empty. How about the polar curve of J? Well, what do you think I'm going to use for my 2 generic generators? The 2 generic generators of J will just be the generators of I. And so that means that the multiplicity over y of gamma 1 of j is just equal to, how about that? It's the multiplicity of IT, O2. The polar curve of this is the zeros of this. And so we're going to get the same answer. And so finally we wind up with the change in E is equal to, on the one hand, it's 0 minus 4, and the multiplicity over y of gamma 1 of j, of I rather, minus the multiplicity over y of gamma 1 of j is equal to 0 minus 4 also. So the theorem checks. So we see that what was sort of happening was that the multiplicity of this polar curve was keeping track of the lack of flatness and the deformation of j. It was making up for that lack of flatness. Okay. So now we want to apply this to the equisingularity of determinantal singularities. Your question?
Can you, maybe you said this, but what is this polar multiplicity of j again? Which number?
Right. So we can even draw a picture here. We take two generic generators of j. These are the generators of I. And so the picture we get for the polar curve looks like this, where these are the zeros of I. And so if we project to C, we get 4 points. But that was exactly the multiplicity of I. So that is it. Does that answer your question?
And in this case, because for t non-zero, the ideal j is the whole ring O2. We
That's
have
right.
everything in the multiplicity.
That's right. Yeah.
If j was deformed less violent, let's say, then maybe some points would be taken
That's
up
correct.
by j.
We have to take some points away then.
Okay, thank you.
So we want to say that a family of determinantal singularities is good if there is a neighborhood U such that Fy is transverse to the rank stratification off the origin for all y in U. This is to prevent certain pathological things from happening. So this means that we only have to look at the strata that contain y. Okay. The other strata don't exist. And also implies that they all have the expected dimension because F is transverse in a whole neighborhood. Okay, so we put our actors on the stage. Remember the determinantal normal module is given by the pullback of the Jacobian module of MT. And that it's easy to show that that means that gamma 1 of n of x is F inverse of the polar of the same codimension of MT. Okay, then we have a nice proposition. Suppose x is a one-parameter stabilization, then this is a crucial thing. The multiplicity over C of this polar curve is actually an intersection number. So this is the result that shows that this invariant, which a priori may depend on the stabilization family, actually does not. So let's see why this is true. So supposing we have the map which defines x, we can arrange for Fy and the polar that we're interested in to be transverse for y not equal to 0. This is an intersection number. It's a number of points in which the image of Fy intersects the polar. It's also the multiplicity over C of the polar curve in the source, because the polar curve in the source is just the pullback of the polar curve in the target. Okay, so now we're ready to talk about one of our first main results. We would like to get our hands on MD. This is one of our goals from last time. We'd like to write MD in terms of invariance that we can compute from X itself. So we have the map which defines a stabilization where our pieces are transverse. We know that if Y is not 0, so here we are working on the stabilization. Because it's a stabilization, we know that the Jacobian module of this guy is equal to this. And so this is going to be 0 for Y not equal to 0. And we can prove that for JZ as well. It's not a big deal. Okay, so that means that when we go to apply the theorem, all we have is this term as far as the multiplicity of the pairs go. The other term is, the subtracting term is 0. So we have the multiplicity of this guy, and that should be the multiplicity of this guy, which we saw was MD. And then we've just seen this is an intersection number, and so we're done. This is an example that I'm going to work out in the problem session that we're going to have tomorrow afternoon. Supposing I have a space curve defined by the minors of this, and we assume that L minus 1 is not divisible by 3. And then we're going to show that M1 of X1 is equal to 2L plus 2. And I've shown what these terms are. We're going to show this about the terms. This term here turns out to be 2L minus 2, and then this intersection number turns out to be 4. This is a correcting factor because of what we're comparing to. And so that gives us 2L plus 2. Let's talk about the W equisingularity of a good family of ides. So suppose we have a good k-dimensional family. Then the family is Whitney equisingular if and only if these invariants here, so the invariants I want are the multiplicity of the pair, and then I also want this intersection number, or the sum of these two numbers, actually. The multiplicity, that's it. There's the multiplicity. Yeah, the multiplicity of the pair plus this intersection number. So I want you to think of these two. This is a sum. This is actually a single invariant. We have one invariant for each stratum, and we're asking that all those invariants are independent of Y. So the proof goes, because you only need to control the strata in the canonical stratification of X minus Y. We see that W holds for each stratum if and only if the fiber of the blowup of this proj is equidimensional over Y. We can show that the bound holds, and this is what I'm going to actually show on the board a little bit. The bound in the fiber of Y holds if these polar curves are empty. And that's the same thing as showing, I claim, that all the MDs are independent of Y. Well, oops, sorry. Yep. All right. This one here. Yeah. The bound in the Y holds if and only if this is empty. That is clear, because if this is empty, The only way this can be empty, it says that there just isn't enough of the fiber of y over y to be hit with the hyperplanes we need. So it has to be bounded then. Now what I want to show is why it is that if these are independent of y, then this polar curve is empty. That's what I want to do next on the board. Okay. And this is a proof by picture. Okay. So this is an example where the polar of codimension D of a two-parameter family is a pair of surfaces. So how do I get this two-parameter family? I know that for each x, I have a stabilization. And I have a family in y. So what I do is I build a two-parameter family, which gives me a stabilization of each xy. That's what I do. That's it. And now, if we look at MD, we see that it's 2 because here are the polars for fixed y. And we see that all along here, there's only 2 sheets. In this example here, this is an example where the number of sheets jumps at 0. This place here is y equals 0. So we had 2 sheets like we had before, but now I've added an extra sheet. This sheet comes in here, but then it goes off here, so it doesn't get counted. So we have that MD at 0, 0 is 3, and MD at y0 is 2, y not equal to 0. Now, this is the key thing, This was a polar of a two-parameter family. The nice thing about the modules and the geometric constructions, if I restrict over to y, then this part of the polar of the two-dimensional family becomes the polar of the one-dimensional family. This is the polar of the one-dimensional family, which is only in y. So what that means is, if the MD is constant, you cannot have a third sheet coming in. They don't exist. And so there is no polar. Notice that we don't count this. We don't count this because this is contained in the singular locus. So we don't have to worry about it. Okay. So that actually proves this result in Whitney equisingularity. Now, the expansion formula in a corollary, we saw back with the ISIS there was an expansion formula. There was also an expansion formula here. And you can use that to say that another result, which is equivalent, is that the expansion formula gives us that So W is going to imply the polar multiplicities are constant, and it's going to imply this term here is constant as well. Oh dear. Oh, we're way behind. Okay. And I just wanted to mention, I came back to this slide because I want to mention that if you replace this with just MD, then this is a result, this equisingularity result is a result that was obtained before by Ballesteros, Bruna, and Tomasella. But our contribution was to work out what MD was, I suppose. Okay, so here's two examples. These are deformations of the Pinkham example. Both families give deformations of the same surface singularity. Both families are Whitney equisingular, but they have different M2 values. The M2 value depends on the landscape. In the rectangular case, it's 8, and it's 6 in the symmetric case. So that means you're not really ever going to be able to come up with a single invariant that is going to control the Whitney equisingularity of all possible families that could be Whitney equisingular, because you'll get different answers depending on which landscape you're working in. Okay. Real brief epilogue. Given this diagram here, suppose V is stable and the normal module for V in the set of allowable deformations is universal. Supposing F0 is transverse to this Whitney stratification of V's, except at the origin perhaps, then we say that X is an essentially isolated sectional singularity. Stabilizations exist because we have the transversality result. E is well defined. And we again can define MD as the degree over C of the polar curve of a stabilization. The invariant is independent of the choice of E because once again, you get the result that shows that you can write it in terms of X. And you define a good family as before. And then you get some nice equivalences. And that is the end. Thank you. Any questions?
So can you come back to the Pinkham example?
Yeah. Oh, go back to the Pinkham example? Okay.
Since I discussed this Pinkham example and projection of it yesterday in my lecture just before you came in. So this is the...
Sorry, there.
So this is the determinantal version. But I think the deformation consists of two different components.
Yes, that's right.
And one of them is three-dimensional. And I only see one parameter there over.
Oh, well, this is not the versal.
It's not the versal one.
No, this is just, if you look inside the versal, you can detect a subfamily, which is Whitney equisingular.
Okay.
That's what I'm doing. These are two distinct families, and both of them are Whitney equisingular.
Yes, but in the one family is three-dimensional.
No, I'm sorry. Maybe I should have said that more. Where we define the singularity here is using the 2x2 minors. We don't use, let's see. Well, let's see. Hold on here. Maybe I'm misunderstanding it. So this is a family of surfaces, so the total family is three-dimensional.
Yes. And
Okay.
the universal deformation space has two components, a one-dimensional one and a three-dimensional one. And I expected to see the three-dimensional also here in the deformation.
Yeah, if you looked at all the deformations, this would have more terms than the other one. Again, you're doing the projective thing though, right?
After that, so I projected this
Yeah.
to C3. So and then you have the same deformation space. This was an old theorem that was the reason I wanted to discuss also Pinkham and
Could you
Cranmer.
say that again? I'm having a hard time hearing.
Hmm?
Could you say that again, please? I'm having a hard time hearing.
Okay, I consider the projection
Yes,
to C3,
yes,
and then you have again deformations with the restriction that the singular set behaves nice,
yes.
and the deformation theory is the same. That is an old statement of Van
Okay.
Straten and de Jong.
Okay,
And therefore, I wanted to point out that there is a relation between this and my lecture.
yeah, yeah, yeah. Actually, I think it's an interesting idea to look at the sort of a generic projection. See, a generic projection should have nothing to do with the projection, but all about the set you're projecting. And so the data you pick up from the critical set is something that you should be able to relate back to the original singularities. And maybe you did that, I don't know.
Further questions? Yeah, I also have a question. One is that I thought that Pinkham's example had the x5 just linearly in the two respective entries. So I was wondering whether maybe there was some switch of variables, or this is a different example which is only related to Pinkham's.
I'm not sure. We got this out of a paper of Johnny Wall's, and he didn't call it the Pinkham example because he was doing a lot more stuff to it. But
Okay. Yeah, okay. There's something with the pluses, but that's I think you understand that you remove the pluses. But then maybe this is another example by
whoops, there's an extra
Pinkham.
plus. You're right.
Yeah, but
I see. I
that's
see.
not the
I'm
point.
sorry that there are definitely typos. Those pluses need to be gone. Oh dear.
Okay, but I have another question to understanding this. So in the equisingularity, you have one parameter for the equisingular deformation, and then the landscape. Can you say that the landscape gives you perpendicular hidden parameter, so that you can in every section you can smoothen and you
Yes.
choose that's
Yes, that's
to
right.
define MD,
Yeah.
and that's how you get different MDs from different matrix structures.
Yes, that's right.
Okay.
Yeah. In
Thank
fact, in these examples, the multiplicity of the pairs in both cases is 0. So the 6 and the 8, the difference between them comes exactly because you're intersecting with a polar of two different, radically different sets. One is the generic symmetric matrices, the other is the generic rectangular matrices.
Okay. If there are no further questions, let's thank Terry for his second lecture.
And thank you for your attention and persistence. I hope in our exercise section
So I continue my lecture about the real singularities. So last time I remind that I presented the Brauer degree, then the Eisenbud-Levin-Kimchashvili formula, and then the Kimchashvili formula for the Euler characteristic of a real analytic function with isolated singularity. So today I will explain what can be done in the case of non-isolated singularities. Okay. And I will present some works that I made here, actually, when I was visited the singularity group in San Carlos. So this is the first paragraph, non-isolated singularity. So I still work with an analytic germ, function germ. And this time I don't assume that the singularity is isolated. So the dimension of the singular set could be whatever we want. So in this case, there is still a notion of negative and positive Miller fiber because IF condition is satisfied. This was proved by my advisor, Karim Becker. So let me present a very easy lemma, but useful. So this is something I proved when I was visiting the singularity group here, but it appeared in the proceedings of the 2018 conference here. So if n is even, then I can relate the Euler characteristic of the negative Miller fiber of F to the characteristic of a link, namely the link of the positive part of F. Yes. So delta is always here delta is positive and small with respect to epsilon. So this is the case n even, and if n is odd, the formula is a bit different. Then we have that the Euler characteristic of the negative Miller fiber of F is 2 minus these things. Okay. So I will prove this one, which is easy to prove, and this one is a bit more difficult, but the spirit of the proof is the same. So I assume n is even. So this is a manifold with boundary, and the boundary is the intersection with the sphere. So the negative Miller fiber is a manifold with boundary. With boundary. Which is exactly, okay. I suppose it is non-empty. I suppose it is not empty. If it is empty, then this is trivial. The result is trivial. So let's assume the boundary is not empty. So what do we have? This is a zero river, the negative Miller fiber. And the ball. So here is the the boundary. So what do we have? So this is odd dimensional. So its Euler characteristic is twice half the Euler characteristic of the boundary. Is 1/2 times the Euler characteristic of the boundary, because it is odd dimensional. Okay. But this part, it is also the boundary of this manifold. Okay, the manifold F minus less than minus delta intersected with the sphere. This bond, the Euler, the minor fiber, but also these things here. Okay, and then you retract. Okay, then you can retract this part to this part. Okay, by integrating vector field like Durfee does in his paper. So this is by retraction. This is no, I was wrong. I have to put this greater than minus delta, and this retract to F greater than 0. Okay. This is the part F greater than 0. Okay. So this is a proof. This is very easy. In the case n is odd, the idea is the same, but I have to consider this manifold, which is a manifold with corner and around the corner, and apply the same trick. So no, why did I do that? Because I have a formula by Safraniak and Bruce for computing these links, the Euler characteristic of these links. So let me present their method. So you take the distance function. I call it omega, the square of the distance function to the origin. X1 square plus xn square. Then if you add sufficient big power of this function to f, you get something with isolated singularity. So this is a consequence of the Loyashevich inequality. So there exists D, an integer sufficiently big, such that so G plus, which is F minus omega to the D, and G minus, which is minus F minus omega to the D. Then these two functions have an isolated critical point. This was proved by Safraniak. At the origin. Okay. So this is a consequence of the Loyashevich inequality. And then Safraniak proved a formula which relate this Euler characteristic to the degree at the origin of the gradient of J plus and J minus. So theorem. So this is due to Safraniak. 86. So I just write the formulas. So the Euler characteristic of the link of the negative part of F is 1 minus the degree at the origin of the gradient of G plus, and for the positive part, we obtain 1 minus the degree at 0 of the gradient of G minus. Okay. So this is a consequence of the formula of Arnold and Wall that I presented on Monday. So now you have everything to get a formula for the Euler characteristic of the minor fibers. Just combine the two results. It's nothing. So corollary. Proved in 2020. So I just put the formula. The Euler characteristic of the negative minor fiber is 1 minus 1 to the n times the index, the local degree of the gradient of G minus, and for the positive minor fiber, we put G plus. Okay. So now, in general, it's difficult to have an estimation of the exponent, but in the case of a weighted homogeneous, we can find it explicitly. Actually, it's not. We don't find D explicitly, but we find another distance function, which gives the result. So this is the method of Bruce and Zafraniak. So let me present it now. So you take, here we work with a weighted homogeneous polynomial. So F weighted homogeneous polynomial, and the type is D1, Dn, and D. Okay. So we have this weighted homogeneous. So we suppose that so I will construct a distance function, so that when we add it to F, we get something with a algebraically isolated critical point, which is more powerful than just isolated critical point. So I take P, let P be the smallest positive integer such that here 2p is greater than D, and di divides P. Each di divides P, sorry. Okay. Then I put AI is divided P divided by P divided by di, and then I define omega by x1 to the 2 a1 divided by a1, etc. xn to an divided by an. Okay. So, for example, if F is only homogeneous, then here this would be D plus 1, or D plus 2, depending on the fact of depending if D is odd or even. Okay. So I define these two polynomials. F1, G1 is F minus this omega. G2 is minus F minus omega, and then G1 and G2 have an isolated, algebraically isolated critical point. This means that the Jacobian algebra is finite dimensional. So G1 and G2 have an isolated, algebraically isolated critical point. So when I was in visiting Sardinia, she gave me a more general proof of for this fact based on finite determinacy. So then we have formula for the order characteristic of the links, and from which we can deduce formulas for the fibers of the weighted homogeneous polynomial. So this is a proof by. So in this case, we have the Euler characteristic of the link of the negative part of F is 1 minus the degree of the gradient of F1, and minus G1 and G2. So as a corollary of my lemma, we get the formulas for the fiber of weighted homogeneous polynomial. So corollary. Then so the other characteristic of the negative fiber of F is 1 minus 1 to the n, the degree of the gradient of G1, and the other characteristic of the positive fiber is 1 plus minus 1 to the n times the degree at the origin of J2. Okay. So in this situation, we can compute, since the critical points are algebraically isolated, we can use the Eisenbund-Levin formula to compute these two degrees. Okay. So now I will explain how we can apply these formulas to the real minor fibration. Okay, so application to the real minor fibration. So I will record some definition and result that César mentioned in his lecture last week. So application to the real minor fibration. So what is the situation? I take a capital F F1, Fk, an analytic map, a germ of analytic map. So analytic. And I assume that K is between 1 and -1. So in general, in this situation, you cannot define a minor fibration. So we have to put a condition. So first I recall the definition. So sigma f is a critical locus of f, the set of points where the Jacobian matrix has not rank K. So this is a set of points in Rn such that the rank, the gradient of Ff1, gradient of Fk is strictly smaller than K. So this is a set of singular points. And then I define the Milnor set. So it was already defined by Cesar and also by Luis Renato. I recall it. This is just a set of points where the sphere and the level of f are tangent. So omega is still the square of the distance function to the origin, and the Milnor set so it is a set of points such that yes, the rank gradient of f1, etc., gradient of fk, and there gradient of omega, which is more or less x, is strictly smaller than k plus 1. Okay, geometrically, it's just a set of points where here you have a sphere and the level of f or f minus 1 over something here, alpha, and set where, and you see here it's a curve. It's a polar curve, but instead of using a linear function, we use a distance function. So it's clear that sigma f is included in the Milnor set. So it's just a remark. So sigma f is included in the Milnor set. Okay. So now I recall the two conditions that Cesar introduced in his talk. There are two necessary conditions to get a Milnor fibration, a real Milnor fibration. So definition. So these conditions were introduced by David Massey. He called them Milnor condition A and B. I will just call them condition A. Just the first singular set is included in the zero level of f. And condition B. So this is this. So Milnor set. Maybe I should write V for f minus 1 of 0. So you take the closure of this set intersected with V, and it should be just 0 in the neighborhood of the origin. Okay, so what does it mean? Imagine you are V here, and the Milnor set here, this is a good situation because the minor set does not accumulate here to V, except at the origin. But for example, it's not so easy to make a picture. But if you have a minor set, imagine something that accumulates here, then this is forbidden. Okay. Here, when you are far from the origin, then in the neighborhood of your point here, the minor set should not accumulate. So, quickly, some examples where these two conditions are satisfied. So, F from K, n, maybe small f. If you have just a function where K can be C or R, then these two conditions are satisfied. So the fact that condition A is satisfied is just it's well known. It can be proved using applying curve selection lemma. And condition B is due to the fact that AF condition is satisfied. In the complex place, it was proved by Lei and Lam, and in the real case by Karim Becker. So this is a first example. Now, second example, when you have an isolated singularity, then the two conditions are clearly satisfied. So when F goes from Rn to Rk, but with an isolated singularity, this means that this set sigma F is just the origin. Then A and B are satisfied. B is triply satisfied because the link intersect the zero spheres, small spheres intersect transversally the zero set. So they intersect transversally, also transversally the nearby fibers. Okay, you have this situation. Then, always by the curve selection lemma, the spheres intersect transversally here at the zero level, but then by transversality, they also intersect transversally nearby a fiber. Here you have a transversal intersection. So condition B is satisfied. Okay. So in this situation, we have a Milnor fibration. This is what César explained in his talk. So from now on, I assume that A and B are satisfied. So F satisfies A and B. So I have to define the Milnor radius. So F is a Milnor, epsilon is a Milnor radius for F. If if this set, yes, if B epsilon intersected with V intersected with the closure of the Milnor set minus V is included in the origin. Okay. Then in this situation, the small level of F intersect the sphere transversally, because we have condition B satisfied. So now let me give the fibration theorem properly. So it was proved by Massey first. And then it was, as César explained, it was generalized to more complicated situation by Tibar, Joita, and also Raimondo and his student Ribeiro. They gave a generalization of this fibration theorem. So Joita, Tibar, Raimondo, and Maicon. So we pick epsilon 0 a minor radius. Then for epsilon smaller or equal than epsilon 0, we can find delta such that we have a tube fibration. So there is delta in R to decay. So delta is smaller than epsilon, such that capital F restricted to the intersection of the ball with the tube, puncture tube. So maybe here I put the dimension. Okay. This is interior. No, maybe it's better to put this. So the puncture, yes. You remove the origin because it is a critical point of, and then you go to the ball. So I guess you do all recognize this result. This is a minor fibration in the real case. So picture, usual picture, 0 level. Here you have the fiber. Okay. This is always the same picture. So, so for example, let me give an example where the fibration is not, there's no fibration theorem. Just take f from R3 to R2, f x, y, z is equal to x square z plus y square and x. So the singular set of f is just the z-axis. So it's clearly included in the zero set. But if you take delta positive, then f minus 1 of delta 0 is not homeomorphic to f minus 1 of minus delta 0, because I think one is empty and the other is not. So you don't have fibration. Okay, you don't have a fibration. So it means that condition B is not satisfied. Okay. Condition B is not satisfied. Okay. So now I will explain how we can apply the formula I gave in the previous paragraph to this situation. Okay. To find some information on the topology of the minor fiber. So now I assume that K is greater than 3, greater or equal to 3. Okay. And I consider a function phi by just removing the last coordinate of f. So phi goes from Rn to Rk minus 1. And it is just f1, fk minus 1. So it's not difficult to check that phi satisfies A and B. A, it's easy. B, it's a bit more difficult, but not too difficult. So phi also has a minor fibration. It is a good exercise to check that. And then there is a question by Manhã in his book, in the chapter 11, where he studies real minor fibration. It was stated only in the case of a isolated singular point. So Manhã's question. So the minor fiber of phi is homomorphic to the minor fiber of f, of the initial mapping, times an interval. So it is not the same delta, but times the interval minus 1 plus 1. Okay. So this is true. It was answered in the case of isolated singularities by Yomdin and King in his PhD thesis in the 70s. So true. So it proved by, so in case of isolated singularity, it was proved by Yomdin and also by King in his PhD thesis. And then in the case of a more generic case of a non-isolated singularity, but with condition A and B, we proved it with Raimondo. And I think it was published in 2016. So the idea, you take this is a minor fiber, and you study the critical point of the last component on this minor fiber. It has no critical point on the interior because of a condition A, but then some critical point can appear in the boundary. And you have to study this critical point and to prove that they don't interfere in the topology. So then, so my formula, the formula I gave before, they concern just function. So here, if k is greater than 3, k minus 1 will always be greater than 2. So what happens if I have only a mapping from Rn to R2? I have to study this case. So So I will consider, yes. Okay, the strategy to prove the minor conjecture, it also works when K is 2. Okay, so the same arguments. Prove that the minor fiber, the two minor fibers of F1, positive and negative 1, they are homeomorphic. To the minor fiber of F1, F2, for example, times an interval. Okay, this is the same proof. It works. It applies also in this situation. And you know that then applying the formula I presented in the first part of this talk, you get an index formula for the minor fiber of for the other characteristic of the minor fiber of this vibration, because it reduces the computation reduces to the computation of a minor of the other characteristic of a minor fiber of just one function. And I explain how we can do and we can compute this in the non-isolated singularity case. So corollary consequence, let's say. Then first we see that the Euler characteristic of the minor fiber of capital F is equal to the Euler characteristic of any of the minor fiber of any Fi, applying this minor question. And then this we can compute, at least in some cases, by what I explained before. So by paragraph 4, you can pick, you can find di such that okay, gi, which is fi minus omega to the di as an isolated critical point, singularity. And this, the Euler characteristic of the minor fiber of capital F is just 1, okay, minus 1 to the n times the topological degree at the origin of the gradient of J. Okay. Then if you work with in the weighted homogeneous case, then you can find something more precise, something with a algebraically isolated critical point. So, remark. If one, it's enough to have one, which is weighted homogeneous. If one of the FIs is weighted homogeneous, then we can get a formula, signature formula for this, an algebraic formula for this. Then we can get, we apply Bose-Zafraniec. To get an algebraic formula, signature formula. for the other characteristic of the minor fiber. And for example, if you take a complex, weighted complex homogeneous polynomial from Cn to C, then you can compute its Euler characteristic using the real part or the imaginary part. This applies in this situation. So I stop here. People have questions?
For the things to work, you need the map to RK minus 1 to define a complete intersection.
What? No, I just mean that the singular set is included in the zero set. And when we are outside the zero set, you have a compact intersection. But this is just a topological condition.
So you are assuming they define a complete intersection then, is that right? Or see, I guess I had a hard time understanding your answer.
What outside the singular set, the rank of the differential is maximal. That's just what I.
Right. So supposing the rank was not maximal anywhere.
This I don't know.
Because what I'm wondering about is if you restrict I mean, in the determinal case, we have a Milnor fiber, right? Because we can take an essential smoothing, and then you can look at the topology of that.
Oh, I see.
So here you could do the real version of that. I mean, if you have the axis, the coordinate axis in space, that's not a complete intersection, and so. But nonetheless, you could still look at a deformation that, by the, it's a determinal singularity. So you look at a deformation that way, and then you can wonder what's going on. The other thing I'm wondering about is that Bookweitz and Groyle, way back in the 70s, I guess it must be, had a paper in the Invenciones where they were able to associate a Milnor number to any curve. That's it. No assumptions about complete intersections or anything. I don't know, is there any possibility of doing anything like that over the reals?
For curves? Yeah, something you can consider is the link. The Euler characteristic of the link can play the role sometimes of the Milnor fiber, of the Milnor number. But
So I only have an observation. So you write W to the power D or DI. So this is a kind of get something in even degree. And it seems that the formula for the Euler characteristic does not depend on D. Is that observation okay? So,
yes. Yes, this means that this stabilizes, I think.
that stabilizes. So yes, so I know the complex case quite well. And then you have Yomden series. And then the Milnor number is going to change linear in D. But of course, here you have real degrees. So that means that, that the type of critical point is going to change, but the index is still the same, independent of D.
For GI?
Yes, so it's not really a question, I think this is an observation. Which yes, I find reasonable, of interesting.
Mhm. Thank you.
It's just a remark that in the real case, the point is exactly to be able to use the formula to compute the degree, right?
Yeah.
By Eisenberg, right? And just a historical remark. We almost can say this is a São Carlos problem because you were here when you did this, and Bruce was here also when he wrote
Yeah.
that paper.
And also with Raimondo, we did this work here. This indoor conjecture.